Welcome to example number 2. We're asked to find the net force on Q1, the charge that is situated between two other charges. The charges are all positioned along a nice straight line, and they're separated by a distance of 0.2 meters from the left and 0.15 meters to the right of the central charge. The outer charges are both negative, while the middle charge here is positive, each showing the amount of charge on each one of them. So, what is the force acting on the charge in the center? The first step in this type of problem is to draw a sketch of the situation, which has already been shown. And we also should probably pick an appropriate coordinate axis. The next step is to draw a free body diagram for this charge Q1, where we've decided to put the origin at that point. You'll see that we have Q2 that is negative and Q1 that is positive, and since those charges are opposite, that will be an attractive force. So let's show the force of 2 onto 1, which would be pulling charge Q1 to the left. If you'd like, you could write this simply as the force of 2, or you could write the force of 2 onto 1. We also see that Q1 has a force that comes from Q3, and once again these two charges are opposites, and so there'll be an attractive force between 1 and 3. So if we were looking at the force of 3 onto 1, that would be pulling this force to the right. So we can label that force as force 3 onto 1, or you can simply write force 3. So what is the net force on charge Q1? Well, that net force on 1, which we'll write simply as F1, would be equal to the force of 3 on 1 plus the force of 2 on 1. But you can see that the force of 2 on 1 is towards the left, and the force of 3 onto 1 is to the right. And if you just wanted to simply find the magnitude, and you'll see that I've dropped the vector signs, and I'll put a negative here because the force of 3 onto 1 is to the right, but the force of 2 onto the 1 is to the left, and we'll put a negative sign in here so that we know that we have to subtract these two forces because they're in opposite directions. And we're assuming to the right is positive, and that's why we've made this force positive, and to the left that force is negative, and hence we put a negative sign there. Now what we need to do is to use Coulomb's law to determine the magnitude of each force. So the force of 3 on 1 is equal to K, Coulomb's constant, times the absolute value of Q3 times Q1, all over the distance between 3 and 1. So I'll write that as R31 squared. Now let's substitute. K is equal to 8.99 times 10 to the power of 9 in Newton meters squared per Coulomb squared. And then we have Q3, which is equal to negative 7 times 10 to the power of negative 6 coulombs. You may not realize that, hopefully. You noted up earlier that 1 microcoulomb is equivalent to 1 to the power of negative 6 coulombs. And you'll see that often that we won't have very large size coulombs. We really often they're to this power, sometimes even a nanocoulomb. So we have that, and we also have 3 times 10 to the power of negative 6 coulombs. And remember that we want to take the absolute value of that so that we can find just the magnitude of that force, because we've taken care of the directions over here. And we're going to divide by the distance between these two charges, which is 0.15 meters, and that quantity is being squared. And after getting my calculator out, I find that magnitude of that force is 8.39 newtons. And you can put the direction if you'd like. You can see that's to the right, so you could just put in brackets over here to the right. If you write that right there with the magnitude and direction, then I guess we're talking about the vector here. So now let's do a similar thing for the force of 2 onto 1. So the force of 2 on 1 will be equal to K times the absolute value of Q2 and Q1, all over the distance between them, R21 quantity squared. Now let's substitute in, and we get the following expression, which leads to an answer of a force of 2.697 newtons to the left. And that's the force of 2 onto 1. So now we're ready to substitute into our equation here. The magnitude of the force of 1 is equal to 8.39 newtons minus 2.697 newtons. And we get a force of 5.69 newtons. Or if you'd like to write it as a vector, the force of 1 is equal to 5.69 newtons, and this would be to the right because we ended up with a positive answer. If we had a negative answer, then that would mean it would be in the direction that is left. And that's it for this example.